Hello everyone, I welcome you all. Today we will be starting with our next topic, that is the stiffness matrix method over here. Okay, now unlike as your flexibility matrix method, this method is also a matrix method in which you have to solve the matrix forms over there. Certain basic equation like as your flexibility matrix will be provided to you and you have to solve the numericals based on that basic equation over there. Right, now stiffness matrix method, as your flexibility matrix method was the force method, the stiffness matrix method is your displacement method over there. Displacement method means what? That is your slope deflection method or moment distribution method. This method will be also displacement method. That means it will deal with the values of slopes and deflections. So the basic aim will be what? You have to calculate the decay, that is the kinematic indeterminacy in your numericals first, or whatever structure is provided to you. In that, if you want to solve it by stiffness matrix method over there, the first initial step will be you have to calculate the decay value over there. Now this stiffness means what? Stiffness, it is the property of your any structural member over there, or stiffness, it is defined as force required to produce unit displacement. Force required to produce unit displacement. Flexibility definition we have seen, that was what? Flexibility was defined as your displacement per unit force. Here stiffness is what? It is the force per unit displacement over here. Right, that means whatever the flexibility and stiffness, these two properties, these are inversely proportional to each other. That is, stiffness is equal to 1 upon flexibility, or flexibility is equal to 1 upon stiffness over there. So if you want to write stiffness in your numerical forms over there, I'll write stiffness is equal to, it is what? It is the force produced, that is, suppose F force is produced over here to produce a unit displacement, and that unit displacement here will be unity over there. So I'll call this D as unity over here. So S is equal to F upon D, that is stiffness is equal to force per unit displacement over here. So here you have to apply the unit displacement. Those will be in the forms of theta and delta. Right. So I'll explain this with an example over here. Suppose I am having any one structure over here, suppose that is a AB, and it is asked to me that I have to calculate the displacement produced over here. Okay, so if you calculate decay value for this, so decay for your fixed support will be 0 and decay for this hinge support or simple support will be equal to 1, right, and that will be equal to theta B. Suppose I assume that it is in a clockwise direction over there. That means what you have to do here, this displacement, that is theta B, that shall be equal to 1, which will produce a force on this member AB to deflect it. Suppose, so I draw the diagram for this. Here I have to apply my theta B is equal to 1. Okay, so if you see the deflection pattern, that will be in this way, which will produce theta is nothing but that is a slope, which will be having this slope value, that is theta B is equal to 1 here, that we assume over here. Okay, so what you have to do here, you have to assume the slopes and the deflections as the translational displacement, and you have to assume those as unity initially. Like as in flexibility matrix method, what we are doing, we are assuming force and moments as your redundants here. Here what you have to do, you have to apply theta and delta as your redundant displacements over here, or that will be called as your non-zero joint displacement. Now we will see for the basic equation for your stiffness matrix method. The basic equation for stiffness matrix method, SMM I'll write. Okay, that is your force produced F is equal to A dl plus S times of D over there. Like as our flexibility matrix method was what? That was equal to D is equal to dr plus F into R over there. Okay, here D was what? That was your given joint displacement over to you. Okay, now instead of displacement what? Here you are having a force value. Okay, here dr was what? That was the displacement occurring due to the given loading to you. Some certain loading was given to you, and whatever displacement due to that loads were coming, that you are taking as dr value for this. For this you are calculating that from a table format over here. Here AD will be what? That will be a force produced due to the given loading over there. Okay, you have to calculate the force produced due to the given loading. For this you have to calculate the friction moments first. That means you have to calculate the friction moments at every joint, and whatever joint you will treat as redundant, those will be your ADL values over there, looking their friction moment values. Next, here F was your flexibility matrix, here S will be your stiffness matrix, and here R was your unknown redundant forces or moments. Here D will be what? That will be your unknown redundant slopes or deflection values. Right? So that will be your basic change in this. Your this basic equation is what? That is F is equal to ADL plus S into D. So you have to use this equation for solving the numericals. Okay, F is equal to ADL plus S into D. You understand these terms very properly. F, those will be what? Those will be your given joint actions. Okay, in this either forces will be given to you, either moments will be given to you, or either couples will be given to you. Same, here we are taking D values. That means if sinking support conditions are given to you, that we are considering here. Here instead of sinking support, here you have to consider the forces and moments if those are provided at the joints over there. That you have to consider under F. Next, ADL is what? Those is the restraint actions. Restraint action means what? You have to calculate the friction moments here. Right? You have to calculate the friction. For that we need to restrain the joints over there. You have to fix all the joints. So restraint action, same moment, forces and couples, whatever you will get. That is, you have to calculate the friction moments for this. Okay. Next, S, that is the stiffness matrix. Here F, that was your flexibility matrix. So S I'll write here as stiffness matrix. And the last term, that is D, it is the unknown, I'll say it as joint displacements. Those will be in terms of theta and delta. Those will be in terms of theta and delta. So these will be your basic unknowns in this that you have to calculate. Whenever you calculate these values, you plot again your slope deflection equations, and then you calculate the final moments over there, substituting this theta and delta values. Okay, so we'll start with the numericals here. Okay, we'll start with this numerical. You have to analyze the continuous beam ABC using stiffness matrix method. Using the stiffness matrix method. Okay, so we'll start to analyze this. Now it is a displacement method. So first step, that will be what? You have to calculate the value of dk here. So first step will be calculation of degree of kinematic indeterminacy. Now you see degree of kinematic indeterminacy at A joint it will be 0 because it is fixed. At B joint it is simple support. So 1 dk will be here, that is theta B, and 1 dk at point C. So here total dk value will be equal to 3, and those are theta B and second is your theta C over here. Okay, both I'll assume in the clockwise direction. Suppose I have to assume those in terms of this basic equation over there in terms of D. So what I'll do here, I'll assume theta B as my D1 and theta C as my D2 value over here. That means at point B you will be having your first coordinate, and at point C you will be having your second coordinate. So what I'll do, I'll mark these 2 points over here at point B and C. So first constant or redundant I am getting at point D1. So here I am marking as my first, that is your theta, and second here again you are having theta at point C. First coordinate it is my at point B, and second coordinate it is at my point C over there. So respectively I have marked my first and second redundants here. Okay. Now in second step I'll write my basic equation over here. Basic equation is, that is what we have, F is equal to ADL plus S into D. Okay. Now what I'll do, I'll calculate these all the values one by one here. Okay. So in that, first I'll calculate the F values over there. Okay. So here first I'll write, that is F matrix. So for F matrix, what you have to do here, you have to see along your first and second coordinate, whatever you have assumed, is there any corresponding force or moment provided to. Now see, here you have assumed theta as your redundant over here. So what you have to do is you have to see whether any external moment is acting at both these points or not. If theta is your redundant, then you have to see whether moment is acting. If you are having deflection over there, then you have to see whether you are having any force as redundant one. So here you have to see any other external force is acting over here, just like as your flexibility matrix method. What we are doing, we were seeing here for D matrix over there. That was what we are seeing there, any external displacement is provided to, that is sinking support condition or not, that we are seeing. Here what you have to see, you have to see whether any corresponding force is provided to at your first and second coordinate respectively. Okay. So here what you have to see, any external moment is acting at point B or C. No, it is not acting. So here your F1 value will be 0 and F2 value will be also equal to 0. Most probably, like as your flexibility matrix method, here also these two values almost comes equal to 0. If any force is acting, then at that time value will come over here. Okay. So here your F1 and F2 values both will remain 0. I'll call this as forces corresponding to the selected coordinates in the given structure. Okay. Forces corresponding to the selected coordinates in the given structure. So our F matrix is completed. Now we are having ADL matrix. So second we'll see for ADL matrix. Okay. For ADL you will be having these two values, ADL1 for first coordinate and ADL2 as your second coordinate over there. Now ADL is what? It is the, we have seen over here in our basic equation, ADL is what? These are the restraint action at point at their selected coordinates, whether you are having forces, moments or couples acting there. That is, you have to calculate the friction moment. So for that purpose, what I'll do, I will restraining all the joints. Restraining all the joints over here. Okay. So here I am having my first member as my AB and second member as BC, and what I'll do, I will restrain all the joints here. Okay. So for this, whatever loading is given to you, that I will show here. Here I am having a UDL of 60 kilonewton per meter and this is your 4 meter. Here I am having a point load of 100 kilonewton, 1.5 and 1.5 meter apart. Okay. So what I have to do, I have to calculate the friction moment values at your first and second coordinate. So if you see, the friction moment value at your first coordinate will be what? That will be your summation of MBA plus MBC. That is, I have to calculate the friction moment of BA and friction moment of BC to get my first ADL1 value. That is, ADL1 will be what? It will be equal to MFBA plus MFBC. Same way here, if I see, here I will be having only one value, that is MFCB over here. So here ADL1 that will be equal to MFBA plus MFBC, and ADL2 that will be your last value, that is MFCB. Or instead what I'll do, I'll mark over here, that is at this point I'll be having ADL1 value. Now if you see, if you calculate MFBA over here, that will be in nature of that will be clockwise, right? Restoring moment we have to see for this. So along this point, this will be having a anti-clockwise moment, restoring moment will be a clockwise. Same way here you will be having clockwise moment, here again you will be having anti-clockwise. So this will be your ADL1, that will for your first member BA, and this will be your AD again L1, but that will be for BC. Okay. And this one, that will be your ADL2, but that will be for your CB value. Okay. So what I'll do, I'll calculate all the friction moments here. So for that, first friction moment I'll be having MF AB, next is your MF BA, MF BC, and last is your MF CB. So from the loadings we will see AB UDL is given to you, so friction moment will be your WL square by 12, but that will be restoring moment will be anti-clockwise, so it will come negative. Here that will be plus WL square by 12, this will come minus WL by 8, and this will come again plus WL by 8, same as your slope deflection method we are calculating this. Okay, so if you calculate these values over here, I have got WL square by W is 60, L is 4 square divided by 12, so I have got this value as minus 80, this I am getting plus 80. Okay, here WL by W is 100, L is your 3, so 100 into 3 divided by 8, so I am getting this as 37.5 and this as plus 37.5, all are in kilonewton meter. Right, now here if I see, I have to calculate the value of ADL1 and ADL2. ADL1 is what? That is, we have selected your first coordinate, that will be for BA and for BC. So here I will calculate ADL1, that will be your MF BA plus MF BC. Same way we have written here, ADL1 is equal to MF BA plus MF BC. So I will substitute these values over here. MF BA I have got as plus 80 and BC I am getting as minus 37.5. So ADL1 here I will get as plus 80 minus 37.5, I am getting this as 42.5 kilonewton meter positive. Okay, same way I will calculate ADL2 value. ADL2, that is your selected second coordinate over here. So for that ADL2 I am getting equal to MF CB. In this diagram you will understand that. So here I will write as MF CB. So I will calculate this MF CB, ADL2, MF CB I am having equal to plus 37.5. Okay, so these two values I am getting, ADL1 and ADL2. Getting? Now we will move to our next step, that is the stiffness matrix. So next I will write S matrix, that will be our having values of S11, S12, S21 and S22. Okay, so one by one we will see. Now like as your flexibility matrix method, you are calculating your F matrix over there. In that F matrix what we are doing, we are applying the unit load at your first coordinate and second coordinate likewise. Right, now here what you have to do is, the thing is, you have to apply the unit displacement at your this selected coordinates over there, because why? Here you are having stiffness is equal to force required to produce unit displacement over there. So for this unit displacement, how much force you are getting, that you have to calculate here. That forces are nothing but S11, S12, S21 and S22. Okay, so in that first I will write apply unit displacement at coordinate 1, keeping remaining coordinates fixed. Keeping remaining coordinates fixed over there. Means what I have to do? I have to apply the unit displacement at my first coordinate and I have to fix the remaining coordinates over there. Now unit displacement that at first coordinate is what? It is nothing but theta b over there. That means what you have to do is, the thing is, you have to apply theta b, that is nothing but we have assumed d1 is equal to positive 1 over there. Okay. Now if you apply this, that means what you have to do is, you have to apply the slope at point b equal to 1. Right. So how we will do this, that I will tell you. Suppose I am drawing this as my member ABC over here. Okay, in that this is A, B and this is your C. Now what they are saying, you have to apply the unit displacement at coordinate 1, means at this point B, keeping remaining coordinates fixed. A is already fixed. Okay, but what you have to do is, you have to fix your second coordinate also. Okay, now you are applying unit displacement at this first coordinate. That means you are applying theta b is equal to 1 over here. How to apply this? I'll tell you. Here first what you have to do is you have to apply the stiffness forces over here. Okay, so here I'll mark the two forces, those I am getting from stiffness over there. Okay, now which are these forces? S of, what is this? Stiffness you are calculating at your first coordinate, right? When unit displacement is applied at your first coordinate, like as F11, F12, those we are calculating. Here we'll get this S11, stiffness at your first coordinate, stiffness value at your first coordinate when you are applying unit displacement at your first coordinate point B over. Here what you will get? S of stiffness value at your C point, that is nothing but your second coordinate when unit displacement is still applied at the first coordinate B over there. That is, this will become S of 2, 1. Okay. Now initially what you have to do, you have to assume these rotations in clockwise directions always. Okay. By solving you will get their actual nature over there. Right. So initially what I am doing, I am assuming this S11 and S21 as the clockwise nature. Okay. Now I'll produce the unit displacement at this points over there. So if I see the unit displacement theta b, I have to assume in the clockwise direction over there. Suppose this is my two members AB and here I am having BC over here, and here I am applying my unit, this stiffness S of 11, same is again at point B but in clockwise nature. So in this way S of 11, and here I am having S of 21 over there. Now you have to apply theta b equal to 1. So theta b will be how? See, remember the thing, the point or the side from which this moment will originate, the point from which side this moment will originate, at that side you have to show this deflected pattern over there. Okay, same way here if you see your this moment is originating from upward side, so your deflection pattern is on the upward side. Here if you see this moment is originating from downward side, so here your deflection pattern will be from the downward side, showing here this slope value, that is d1 is equal to 1, that is nothing but theta b equal to 1, and here also it will show d1 is equal to 1 here. Okay, so if I draw a combined diagram for this, how that diagram will be? For BA member it will be on the upward side, and for BC member it will be on the downward side, which will show this overall deflection, that is d1 is equal to 1, that is nothing but theta b equal to 1, and here again d1 equal to 1. That moment will not be coming at your second restraint joint, because why? This is the restraint for the slope value. Okay, so here you will be having d1 equal to 1, or you can write theta b is equal to 1 also, that is also okay. Getting this? So in this way you have to draw this deflection pattern over there. Now we'll see for the values of S11 and S21. So here S of 11 value. Now your unit displacement that is applied at your first point over here, right? That is you are having here near end and far end concept. So if unit displacement is at point B, so this joint will be your near end joint, and near end joint will be having here rotations of 4 EI theta upon L, and that theta will be your theta b value, because we are seeing for theta b. Okay, but here if you see this S11 value, those are for two members, that is for BA and for BC, means it will be a near end for two members, that is BA and BC. So this value S11 will be equal to summation of 2, that is first one for BA plus again 4 EI theta b upon L, that will be for BC. Okay, so we'll substitute here values over there, that is 4 EI theta b value here that we are taking equal to 1. Okay, so divided by L, EI is given to you constant, so keep it as it is. So what will remain? 4 EI upon L of what? That is for member BA, it is provided to equal to 4, plus here you will be having 4 EI again theta b is 1 divided by L of member BC, that is provided to equal to 3. So 4 by 4 this will become 1 EI, and this 4 by 3 that will become equal to 1.33. So this total value you will get equal to 2.33 of EI, that will be your S of 11 value. Okay, so here S11 I have got over there. How we have calculated this value? Again you see S11, that is the combined moment action for BA and BC. Okay, so here if you are applying unit displacement at your first coordinate and moment calculation or S11 you are calculating at that particular coordinate only, so that will be your near end. Okay, simple. What you have to do at the point where you are applying the unit displacement, if you are calculating stiffness value at that point, that will be your near end. You just remember this. If you are calculating stiffness at a particular point and there you are applied unit displacement itself, that will be your near end, and the remaining other any point will be your far end over there. So S11, it is the combination of BA and BC moment. So here S11 will be equal to 4EI theta upon L, near end moment rotation value 4EI theta upon L, that is for BA, plus 4EI theta upon L again for BC. So if I calculate that value, I am getting that equal to S of 11 equal to 2.33. Right, now I'll see for the value of S of 21. Okay, here you are applying unit displacement. As compared to this unit displacement, this point C will be our far end over there. Okay, but that is subjected to only one member, that is CB. So S of 21 will be equal to far end rotation, that is 2EI theta B upon L. It will be only theta B here, because why? For theta B this will be treated as your far end. If you consider theta C over there, that will be your near end. Right, so here for theta B it will be far end, that is for member CB, or you can write BC also. So if I substitute these values again, this I'll get as 2 EI theta B is again 1 divided by L of CB, that is your 3. So S of 21 I'll get this as 2 by 3, I'll get this as 0.67 of EI, 0.67 of EI. Right, so S of 11 I have got, S of 21 I have got. Now I'll move to my next part, that is Roman 2. This was for what? When I have applied the unit displacement for your first coordinate. Now second, what I'll do, I'll apply unit displacement at coordinate 2, keeping all other coordinates fixed. That means what I have to do, now I have to free my second coordinate and I have to fix it at my first coordinate over there. So I'll draw the diagram again. A will be fixed, B will be also fixed over here. Remember, in this diagram you have to not take the loadings given to you. Loading already that we have calculated values ADL1 and ADL2. Here in this you have to not take the loadings concept, only just you have to take the members. Okay, so here this will be your joint A, B will be also fixed, and C will be now free over here. Right, so again first what I'll do, I'll mark my stiffness coefficients over here. So those I have told you, always assume those initially in a clockwise direction. Okay, so here first what I'll get, S of, right, stiffness you are calculating at point C, that is your second coordinate. So S of 2 when unit displacement is applied at your second coordinate, because what, you are applying unit displacement at coordinate 2. So this will become S of 2. Next, S of, what this will become, stiffness you are calculating at point B, that is your first coordinate, when unit displacement is applied at your second coordinate. So this will become S of 1, 2. Okay, now here what you have to do is you have to apply unit displacement at coordinate 2. That means you have to apply theta C or D2 is equal to 1 now. That is your second coordinate, theta C you have to assume this. So you have to apply this equal to 1 there. Okay, so if I see this pattern for this deflection pattern, this is a clockwise moment originating it from upward side. So how that deflection pattern will be, that will be from the upward side, which will show this value, that is D2 is equal to positive 1 now, or you can say theta C is equal to 1 there. Now I'll calculate these values, that is S of 1, 2 and S of 2, 2 over here. Okay, first 2, 2 value I'll calculate. See, S of 2, 2, you are applying unit displacement at your second coordinate and this moment is also acting at the second coordinate. So this will be treated as your near end. So that moment will come 4 EI theta C upon L, but theta C is what? That is your equal to 1 here. So simply what I'll get, 4 EI upon L. L of what? That will be for member CB. So for member CB, this is your 3. So S of 2 2 I am getting here equal to 4 by 3. I will get this as 1.33 of EI. Right? Next, S of 1 2 I will calculate. You are applying unit displacement at point C. Compared to this, B will be your far end over here. Okay. So for far end moment, that will come here 2 EI theta C upon L, but this will be only for member BC. Now you see here, you will get confused over here. S11 we have taken for two members, that is BA and BC, because it was acting rotation at point C, at point B. Okay, but here S of 1 2 that will be only for member BC, because why? A and B both are here completely fixed over there. Okay, if A and B are completely fixed, this total member will be restrained for the all the joint displacement, that is theta and delta. So your this near end value for BA member, that will become 0, or theta here will become 0 for BA member. So this will come only for BC. So 2 EI theta is again 1, L is your for BC it is equal to 4. So 2 by 4 this will become equal to, sorry, your BC is 2 EI theta is again 1 divided by length of BC is again 3. So this will become 2 by 3, that is 0.67 of EI. Now you see your this S12 value should match with your S21 value. Check, this you are getting 0.67, here also you are getting 0.67. Okay, your analysis here is going in correct direction. So all the values now I have got here. Now what I will do, I will substitute all these values in my basic equations over there. So basic equation is what? That is F is equal to ADL plus S into D. Okay, F values both I have got 0 is equal to ADL values. Okay, ADL1 that is MF BA plus BC, and ADL2 that is your MF CB. So this I am getting as 42.5 and 37.5 both positive. 42.5 and 37.5 plus S values. Okay, in S values if you see, all are multiplied with EI over there. Okay, so what I will do, I will take EI common from all these values, right? So S of 11 that I have got as 2.33. Next S of 12 0.67, again 0.67, and S of 22 I am getting as 1.33. In this matrix you have to substitute these values, S matrix. Okay, multiplied by D, that is nothing but redundant values D1 and D2. Okay, so if you again solve this for equations over there. Okay, so what I'll get this equation as, suppose first 0 is equal to 42.5 plus EI is multiplied to this. So what I'll get, EI common from this. Okay, so this I'll get as row multiplied by again column 2.33 of D1 plus 0.67 of D2. So if you simplify this, what I'll get, 2.33 of D1 plus 0.67 of D2 is equal to this. After going to LHS side, that will become negative 42.5, and this EI will get divided to this. I'll call this as equation number 1. Same way, if I'll solve for second equation, what I'll get, that 0.67 of D1 plus 1.33 of D2 is equal to this. After going to LHS, that will become minus 37.5, and this EI common will get divided to this. This will be my equation number 2 over here. Okay, so if you solve this 1 and 2 for the values of D1 and D2, I get D1 and D2. D1 is nothing but your value of theta B, D2 is nothing but your value of theta C. I have got D1 is equal to minus 11.84 divided by EI, and D2 as minus 22.22 divided by EI over there. Now what this minus is indicating here, what this minus is indicating, initially what we have done, we have assumed this theta B and theta C in the clockwise rotation directions over there. Okay, you are getting final answers those as negative. That means what, these will be acting in anti-clockwise directions over there. Okay, so this will be our basic unknown values over there, D1 and D2. That was our basic aim over there. Now you have to calculate the support moments over there from this. Okay, so for that, next step will be what, your step number 3 it is, that is you have to do is the slope deflection equations. slope deflection equation. Now for first member I'll see MAB is equal to, okay, MAB, that is what, slope deflection equation. We take always your MFAB value first, plus 2EI upon L into bracket is near end rotation, but for near end rotation theta A will be 0, so here that will become 0. What will remain? Just theta B. Okay, so if you solve this MFAB, I have got that as minus 80 plus 2A upon L. L here is given to you 4, so 2 by 4, that will become equal to 0.5 of theta B as my equation number 1. Okay, next for in this equation now same I'll substitute the value of theta B over here. So theta B, if I substitute that equal to minus 11.84, I get MAB is equal to minus 85.92 kilonewton meter. Okay, now I'll move for my next value, MBA. MBA is what? That is again MFBA. Directly values I'll write. MFBA I'm getting as plus 80 plus 2A upon L, that will become again 0.5 into bracket 2 times of theta B now. So if I substitute again theta B over here, I get MBA is equal to plus 68.16 kilonewton meter. You check these values over there. Okay. Next, I'll see for my next value, that is MBC. MBC, that is again MFBC plus 2EI upon L into bracket near end rotation. Near end is B, far end is C. So this will become 2 times of theta B plus theta C. Delta values for all will be 0 because there is no any sinking support condition provided to, right? So this, if I substitute MFBC I am getting as minus 37.5 plus 2A upon L. L is your for BC 3. So 2 by 3, that will become 0.67 of EI into bracket 2 theta B plus theta C. So here you substitute theta B and theta C, both the values. I am getting MBC as minus 68.16 kilonewton meter. And last MCB, that will be your MFCB. It is 37.5 plus 2A upon L, same, that is 0.67 of EI. Here what will happen? Near end and far end will be revised, that is theta B plus 2 times of theta C. So if I substitute again theta B and theta C, I have got MCB is equal to 0. MCB is equal to 0. Now we'll check our conditions of equilibrium. So if you apply condition of equilibrium at joint B, that will be what? MBA plus MBC, that shall come equal to 0. Check whether you are getting satisfied. MBA plus MBC, 68.16 and minus 68.16, that will become 0. Okay, first condition is getting satisfied. Second condition will be at point C, that will be what? M of CB, that shall come equal to 0, because why? This will be treated as your incapable support. So for incapable support, moment at this point shall come equal to 0 over there. So check it. Okay, we are getting that again 0, right? So here your numerical gets conclude, and then we'll plot your bending moment by superposition order A, B, C. Okay, for A I am having this as minus 85.92, minus it is, so it will be plotted on the upward side. 85.12, same sign conventions you have to use, negative, positive, positive and negative. That is for beams I have told you. Okay, next BA, you are getting positive over here, 68.16. Okay, and next here you are getting equal to 0. Just what you have to do is you have to join this by a straight lines over there. Now this will be your support moments. We'll plot the span moment over there. So span moments will calculate first. In that span moment, first is your AB and second is for BC. In AB, UDL is provided to, so that will be your WL square divided by 8. Okay, here UDL is provided to, so that will become WL square divided by 8. W is 60, L is 4. So 60 into 4 square divided by 8, I am getting that equal to 120 kilonewton meter. And in span BC, a central point load is provided to. So for a central point load, this value comes equal to WL by 4. W is 100, L is 3. So 100 into 3 divided by 4, I am getting this value as 75 kilonewton meter over there. Okay. So in portion AB, UDL is given to you, that is of 120. So that will follow a parabolic path. This is your 120. And in portion BC, point load is provided to you of 75 span moment you are getting maximum. So 75, that will follow triangular path maximum at the center. So this is 75, that is WL by 4, and this is 120, that is WL square by 8. Just what you have to do is you have to shade the superimposed part here, and that will give you BMD by superposition. Okay, so this will be our total numerical for stiffness matrix method over there. Okay, just what you have to do is you have to calculate the first step decay. In second step, you have to do the basic equation, and from basic equation, whatever matrix you are getting, F matrix, ADL matrix, S matrix, and D matrix, you have to solve all those matrix, and finally you have to calculate the basic unknown values over there, that is decay values. Okay, and these decay values you have to substitute in the slope deflection equations to get this the final moments over there. And what you have to do is you have to plot BMD by superposition from obtained final moments here. Okay, if you are having any doubt, if you are having any query, you can comment me. Thank you so much.